Let us continue with the acceleration level analysis. Before we get in there, I want to make a remark, so I made some room for the remark here. If you recall from in the velocity level analysis, we had this term. Let me mark it for you. This one right here. This one right there. ddt in 1 of p04. Let's look at that term a little closely and remember the definition of velocity of a point from our lectures. So I am going to claim that the velocity of the point B in the first frame is equal to ddt in 1 of the vector p04. Again, the velocity of point B in 1 equals ddt in 1 of p04. Why is that? Let's go back to our figure. Okay. P04 is a vector that goes from O1 to B. Let's remind ourselves of our definition of a velocity of a point. To calculate the velocity of a point B, of the point B, what we need to do, suppose we want the velocity of the point B in frame 1, okay? What do we need to do? We need to take a point that is fixed in frame 1 and then draw a position vector from that point to point B and take the derivative of that vector in the frame 1. That is exactly what we are doing when we are doing ddt in 1 of p04, because the point O1 is fixed in 1, as it is fixed in 0, but it is also fixed in 1. So the point O1 is fixed in 1, and the vector p04 goes from that point to point B, right? And then we're taking that vector and taking the derivative of that vector in frame 1. So it exactly fits our definition. So what we can call the ddt in 1 of p04 to be the velocity of the point B in frame 1. Okay, so I'm just doing this so I can write VB in 1 in our equations and simplify the appearance of the equations pretty much. Okay, very good. And I should say here, this is by the definition of the velocity of a point. Velocity of a point. So if you don't remember the definition, please go back to our lecture slides. It's given there, okay, or in the textbook essentially. Okay, once I make that remark, let me put a square here to signify the end of the remark. I should also say that I went ahead in Julia and solved the linear system above, this linear system. I inserted the numbers, and the output came out to be something like this. Theta 1 dot came out to be negative 95.3 radians per second. Theta 3 dot came out to be 120.7 radians per second. D4 dot is a large number, but this is because it's millimeter per second squared. If you convert this in meters per second, sorry, this is because this is millimeter per second. If you convert it to meters per second, it's clearly going to be 72, which is reasonable. D5 dot came out to be negative 39,600 something in millimeter per second units. Okay, that is the end of the velocity level analysis. To do, here we start the acceleration level analysis. To perform the acceleration level analysis, let us remind ourselves of the velocity level equations in vector form. I marked them here with double stars. The first velocity level equation in vector form will be this one. The second velocity level equation in vector form will be that one right there. Okay, so let me pull all those things down here, at the end of the document, and make it acceleration level equations. So I'm going to take this guy, if I can. This is going to be difficult to take, but let me try. Take this guy, copy, paste, This is one of them. We'll modify it in a second, or a couple minutes at least. And we are going to take this particular one here. Let me see. Oops. Yeah. Okay, let me try it again. Sorry. Okay, copy. Okay, there we go. Paste. Great. Okay. So let us modify these slightly. What did we say about this term here? We said that term was the velocity of the point B in frame 1. So let us replace that with that. So I'm gonna erase this, delete, and call it velocity of the point B in frame 1. Great. This one is 0, we said, so we can get rid of that. This one here was 0, so we can get rid of that, delete this one as well. Okay, so these are our velocity level equations. The first one in simplified form. So let's put it there. And let's go down to the second one. This one is 0, so we can delete it. This one is 0, so we can delete it right there. Okay. Very good. And if you recall, this one here is the derivative of the vector that goes from the fifth frame to the second frame, ddt in 0 of p52. And so let me write that. So this one here was ddt in 0 of p52. If you observe the figure again, let's go back down here, up here at least. The vector that goes from 5 to 2, right? Let's think about that vector. That vector goes from D to O2, right? O2 is a point that is fixed in the world frame, right? So if I consider the vector negative p52 and the derivative of that in the zeroth frame, that's going to give me the negative of the velocity of the point D in frame 0. Or we can think about this the other way around. So the point D is a point fixed in the fifth frame. So we are talking about a position vector that goes from a point fixed in the fifth frame to point O2, right? So, and we're taking derivative of that in the zeroth frame. Now, if we go back and take the derivative in the fifth frame, using differentiation in 2 frames formula, since the fifth frame doesn't rotate with respect to the zeroth frame, right? The first term in that differentiation in 2 frames formula is going to vanish. And essentially, that's going to be velocity of the point O2 in the fifth frame. Anyway, so let me try to wrap this again. So I'm going to use the first discussion that I made here. Let me go back here. So what I'm going to do is the following. Okay, so I'm going to take this guy, make some computations here. ddt in 0 of p52 is equal to ddt in 0 of the position vector that goes from D to O2. Okay? The position vector that goes from D to O2. The position vector that goes from D to O2 is equal to the negation of the vector that goes from position vector that goes from O2 to D. Yeah? I can take the negative out. ddt in 0 of P02D. Yes? O2 to D. And now I realize that this is a position vector that goes from a point fixed in the zeroth frame to a point D that is moving in the zeroth frame. And I am taking the derivative in the zeroth frame as well. So I recognize this to be equal to negative of the velocity of point D in the 0th frame. Okay? Is that clear? So I'm going to essentially replace this one over here with that term right there, so that the equations look nicer, and it's more succinct to write, and it's more succinct to take the derivative of, which is coming up. Okay, with this discussion out of the way, now I'm going to take this whole thing here, delete it, also delete this actually, and replace that with, as this calculation here suggests, replace that with negative velocity of point D in the 0th frame. Okay? D looks really like a 0, so let me try it again. Point D in the 0th frame. Okay, let us move these things over here as well. And this one can stay here for your future reference. Let me draw a box around it so it doesn't interfere with our other calculations. Okay. Now, these are the simplified, this one and that one. They are the simplified versions of our velocity level equations. But to do the acceleration level analysis, I need to take the derivative of these equations in the 0th frame. Okay. I must take this derivative. All right, very good. So let's do it. So let's call this well, yeah, let's give this a name. For now, let's call it A1. Let's call this one A2. So when I'm taking the derivative, I can refer to them by those names. Okay, let's go to the next page just to avoid clutter, and let's start working actually on A1. So I need to take the derivative. I need to distribute the derivative first. So let's do that. d dt in 0 of velocity of point B in 1 plus d dt in 0 of angular velocity of 1 in 0 cross P04 plus d dt in 0 of the angular velocity of 2 in 0 cross P42 equals 0. Okay. Now, for this term, I'm going to use differentiation in 2 frames formula, and I'm going to differentiate that guy in the first frame. Okay, so let's do that. The first term is going to be d dt in 1 of the velocity of the point B in frame 1 plus angular velocity of 1 in 0 cross VB in 1. Yeah. Then I come to the second term, right? This one right there. Sorry about the zoom in and out. Sometimes it catches my fingers. So I have to rectify it. Okay. Anyway, so this term over here, I see a product term. Whenever I see a derivative of a product term, I must use the product rule of differentiation clearly. So what I'm going to do is exactly that. d dt in 0 of angular velocity of 1 in 0 cross P04 plus, oops, okay, oh my god, I messed up the 4. P04 plus, it started raining heavily, so sorry about the raining noises. Angular velocity of, oh wow, that's the electricity that went and came back. Angular velocity of 1 in 0 cross d dt in 0 of P04 plus d dt in 0 of angular velocity of 2 in 0. Oh, sorry about that. Okay, let me end the video here and I'll talk about that in my next video. Okay, I'm sorry about the interruption. Let me pick up where I left off. So we were talking about how to take the derivative of this piece here, or how to evaluate that derivative essentially. And we said that that's a product term, so we need to use Leibniz's rule of differentiation, or product rule of differentiation. So I'm going to apply the derivative on the first term first, cross P04, plus leave the first term alone and apply the derivative on the second term. Great. Okay. And finally, the last term, the last derivative, we need to take that derivative as well. So again, product rule of differentiation, d dt in 0 of angular velocity of 2 in 0 cross P42 plus angular velocity of 2 in 0 cross d dt of P42 equals 0. Okay, let's try and simplify this equation. Let's start working on the first term here. The first term is the derivative, the time derivative of the velocity of b in 1 in frame 1. If you go back to our lecture slides, this is exactly the definition of an acceleration of a point. This we can call the acceleration of b in 1 plus angular velocity of 1 in 0 cross velocity of b in 1 plus, and this term here, derivative of the angular velocity of 1 in 0 is by definition the angular acceleration of 1 in 1, and we denote it by alpha. Okay, again, these definitions are present in the lecture slides or in the textbook. Cross P04 plus angular velocity of 1 in 0 cross, now this guy, derivative of P04 in 0. We took that derivative in the velocity level analysis. If you go back, then bear with me as I find that. Check this term out right here. That's exactly the same derivative as we are trying to take over in the acceleration level analysis. So what I'm going to do is use this result here, this one and that one, right? That was the derivative that corresponded to this derivative here. So if I just go ahead and replace that, and the first term we said was velocity of b in 1 plus angular velocity of 1 in 0 cross P04. Okay? So I just went ahead and replaced that because we have done that derivative already. So carrying on, the bottom line of the top equation here, I need to take that derivative, but that is by definition the angular acceleration of 2 in 0 cross P42 plus angular velocity of 2 in 0 cross this one here, which is the derivative of in 0 of P42. And again, we did that in the velocity level analysis. If you go back here, yeah, right here, this term here, this one here, is given, the derivative of that is given right here. So I will take that, borrow that, and since the first term there, this one is 0, I'm just going to borrow the second term right there as a derivative. Okay, so this is going to be angular velocity of 2 in 0 cross P42 equals 0. Very good. And now the final step is that we can collect some terms together. So let me put some continuation signs here so you can follow more easily. This is going to be the angular velocity of b in 1, acceleration of the point b in 1, plus we have a angular velocity of 1 in 0 cross velocity of b in 1 term here, and another one of that right there. So we can join those together to say 2 times angular velocity of 1 in 0 cross velocity of b in 1. Okay, so this is 2 times angular velocity of 1 in 0 cross velocity of b in 1. Two of those. Plus, I have angular acceleration of 1 and 0 cross p04 plus angular velocity of 1 and 0 cross angular velocity of 1 and 0 cross p04. That's the one term remaining from this computation. If you remember, we borrowed one of those terms to put that over together with that term right there. Okay, very good. Plus angular velocity of 2 in 0 cross p42 plus angular velocity of 2 in 0 cross angular velocity of 2 in 0 cross p42 equals 0. And this is as simple as it gets. Now, let me make a few remarks over on this computation right here. So my first remark is going to be about these terms right there, okay? The placement of the parentheses on these terms is absolutely crucial because if you try to put the parentheses this way, this is equal to 0. Why? Because you're taking the cross product of the same vectors. And the cross product being antisymmetric means that the cross product of the same vector is equal to 0. However, if you write it this way, if you're talking about this computation, this is definitely non-zero. How do I know? Well, because if you take the cross product of two vectors, this is the result is perpendicular to both angular this vector and that vector. Well, then you're taking the cross product of a vector that's perpendicular to that vector with that vector, which means that the result cannot be 0 unless one of these terms themselves are 0. Is 0. One of these terms itself is 0. Okay? So that's the first remark. Let me erase those parts. Okay. Similar remark goes for this term, of course, right? You cannot change the order of multiple cross product. That's the important bit. Okay, the next remark that I want to make is that from your dynamics class, engineering 220, if I recall, may not be correct, so don't quote me on that. But from that class, you might remember what is called a centripetal acceleration and the acceleration of a point, and has a centripetal term. And that centripetal term actually are exactly these terms. These terms are centripetal or Coriolis. Sorry, not Coriolis. These terms are centripetal accelerations. This one and that one, they are centripetal accelerations. The Coriolis acceleration actually is hidden right here. This is called the Coriolis acceleration, that term. Okay? And Coriolis acceleration happens when something moves on some other body that's also moving to a fixed body. That's the Coriolis acceleration term right there. Okay? Very good. So we've covered a lot. This is the acceleration equation that corresponds to the first vector loop. And we still have to work on the second vector loop, so let me not waste any time and work on that. So I'm going to use that guy right there. So since I cannot see it as I'm working on it, I'm going to copy it then down under, and I'm going to erase it when the time comes. Okay, paste. Okay, so this is what we are working with. So I'm going to distribute the derivative operation over the summations, or plus and minus signs. Yeah. So we have ddt in 0 of angular velocity 1 and 0 cross p03 plus ddt in 0 of angular velocity of 3 and 0 cross p35 minus ddt in 0 of velocity of d in 0. This is all equal to 0. Okay. Once I've distributed that, I no longer have any use for this. So let's delete that. Okay. Again, here Leibniz rule, here Leibniz rule, and this is already immediately recognized as the acceleration of point 2 in 0. Yeah, so let's go back. Okay, apply the Leibniz rule. This is going to be d dt in 0 of angular velocity of 1 in 0 cross p03 plus angular velocity of 1 in 0 cross d dt in 0 of p03 plus, now I'm over this term, d dt, again, Leibniz rule, angular velocity of 3 in 0 cross p35 plus angular velocity of 3 in 0 cross d dt in 0 of p35 plus, or sorry, minus this term here. As we said, this is exactly the acceleration of point d in 0. Okay, let's do some more computations. d dt in 0 of angular velocity of 1 in 0 is defined by angular acceleration of 1 in 0 cross p03 plus angular velocity of 1 in 0 cross this term here. We computed this derivative in the velocity level analysis, and I'm just going to write it down here. This is equal to angular velocity of 1 in 0 cross p03 plus, again here we have angular acceleration of 3 in 0 cross p35 plus angular velocity of 3 in 0 cross, we did this derivative over in the velocity level analysis again as well, and that is what? Angular velocity of 3 in 0 cross p35. And finally I have the acceleration term here, it's equals 0. And that one here is as simple as it gets in vector form. So this equation here, tick, 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 3 stars, as well as this equation here, 3 stars, they are the vector, they are the acceleration level equations in vector form. Acceleration level kinematic equations in vector form, okay? And once we have these equations, our task then is to go back and express them in the zeroth frame. Let me do that in the next video.